Yeah, because somebody is supposed to remind me, and he's not even here to remind me. Okay, guys. Any questions on memory management? No. Good. So what's the problem with the fixed partitioning system? Disadvantages of fixed partitioning system.
Internal fragmentation.
It suffers from internal fragmentation. And what's the problem of the dynamic partitioning system? It suffers from dynamic, external fragmentation. What's meant by best fit allocation of memory? Can you describe best fit allocation? Anybody?
Start to top to bottom, and we saw the values which is the best.
Exactly. You search the free tables partition or table. You search the free table from all the way from top to bottom and guess and find out which one is the smallest partition that we can make allocation from. Okay, and what's the advantage of the best fit? Does it give better or worse use of memory than the first fit?
It gets better.
It gets better. And does it give better, faster allocation or slower allocation than the first fit?
No.
What? No is what? Faster or slower?
No.
Slower. And that's its disadvantage. Okay, very good. What else did we talk about? What kind of information you'd expect to see in the base register? Base register, anybody knows what the base register contains?
It starts after the operating system.
It's the starting address of the code, of the process. What's the difference between a process and a program? Any idea? No? Give other people a question. Thank you for studying. It's the guy behind you. Yeah, go on.
Process is program execution.
A process is a program in execution. What about, what's meant by relative address? Is it same as physical address? What's the relative address? Do you remember? Where is the 0 point of a relative address? Is it the same as the physical 0 point in main memory? Relative address? So it refers, its relevance to only the code of the program. First line of code is at location 0. The physical address is the address in memory. So if we put this code in memory in a different location, then every time the program say go to location 100, it actually means 100 plus wherever it is located in memory. It has to be corrected to its physical address. How does the dynamic partitioning system stop a program from accessing memory area that belongs to another program? I know it does, it protects programs from others, but what does it actually do? How does it know every time a program say modify this space in memory, whether to allow it or not? Any ideas? Okay, there are two registers. It checks the base register and another register. As long as the space, the address that needs to be changed is between the addresses in those two registers, it will allow it. Any idea? No, you don't remember this? Okay. Let's see if I can. If this was memory, then memory has addresses all the way from 0 to the maximum. Let's say 4 gigabytes. And this is called physical address. So anything, any address referenced in memory, it's physical address. If we have a program, when you write a program, the code starts from the starting of the program 0. So when you reach 1, 2, 3 lines, for example, just go at line level, line 100, line 200. So if I say go to location 100, this is, they call this relative address. Relative to the start of the program. So it's easier to get every programmer only worry about your code. Your address is always starting at your location 0. But if I say here, go to line 100, you know, the programmer means line 100 here. That's called relative address. But if we put the code here at location 2000, for example, and the program is running here, and if the program says go to line 100 or memory location 100, it doesn't mean 100 there, because that'll be outside its code. But everything is added to the starting point. So it means from now on it's going to be 2100 when it's in here. So the memory manager will keep adding this number to every address that the program brings. So the program generates relative addresses, but they're corrected in memory. If we had put this program in location 1000, then it will be corrected by adding 1000 to it. The memory manager, when it puts the program here, it tells the program you have base register. So it takes this number and puts it into the base register. So the program, it always starts at, it looks at its base register. The base is the starting point. And the maximum point for this address, the last address, is put into another register. Anybody knows the name of that register? The bounds register. So any address to be modified, the memory manager would check, is it between the address saved in the base register and the address kept in the bounds register? If it is, then it will allow it, it's in here. If we move if the program is in another location, then that would be its base and that would be its bounds register. So the relative addresses don't change. The programs always call, it's like local addresses. But that local address, once you are actually working in main memory, it has to be corrected all the time to the exact, and that final address in memory is known as the physical address. Have you noticed something? I was writing back to front, from right to left. Or is it my imagination? I think there's something that needs to be swapped. Let me find out how to do that. I think it's in possibly the video setting or something. Anybody knows where to swap the mirror effect on this? Video filter, is it here somewhere? General, can you see the word mirror effect now? Video. Mirror, there it is. Okay, I hope it's fixed. Is it fixed?
Yeah.
Right. Guys, you see something not showing right, let me know. Because it's going to be, that's what you're going to see in the video. Okay, so that's really. So which one is better? The fixed memory management or the dynamic memory management? The what? Dynamic. That's a good answer, right? It's the wrong answer though. Any idea which one is better? The fixed. It sounds also like a very good answer. It's wrong answer. Okay, anybody wants to take it up? Which one is better? Fixed or dynamic partitioning systems? I know the dynamic is the modern one, but at that stage. And the fixed was the real first one. So which one is better, did you say?
Fixed.
The fixed. No, it's wrong answer. Which one is better?
It depends.
Exactly. Guys, anytime I ask you, or anybody asks you from now on, anything about technology, which one is better, A or B? Never say A, never say B. You say, well, sometimes A is better in this case, and you give the reasons when A is better. And also, B can be better in those circumstances. So, why sometimes the fixed partitioning is better? Anybody knows? One reason why the fixed partitioning is easier or is better to use. It's less complicated. It's simpler, easier to program. And it doesn't suffer from fragmentations, right? Pardon? It doesn't suffer from external fragmentation. While the dynamic partitioning, can you give me one good reason or bad reason? The dynamic partitioning. It has?
External fragmentation.
It suffers from external fragmentation. And it's a little bit more complex than the fixed partitioning. Remember, if a program comes in and asks for memory, and we give it memory, and then it finishes, then we deallocate. Memory is deallocated. Anybody knows what's involved in the fixed partitioning deallocation process? If a program finishes memory, what does the memory manager do to the freed memory? The memory that has just become free in the fixed partitioning. Any idea?
It overrides the program.
It overrides the program, the code, right? It goes and wipes off the code. No, it doesn't. Anybody else? Pardon? It marks it free. Where does it mark it? In main memory? In a table. So the dynamic partitioning system has all these partitions in a table. The address of the partition, the size of the partition is busy or free. So it just goes there and marks it. In the fixed partitioning, it just marks it as free. What about the dynamic partitioning? What's involved in the deallocation? Any idea? Deallocation of memory in dynamic memory management? Any idea? No? Hey guys, you better start studying. I know, memory manager, this is the toughest part of the course. We're nearly finished. Maybe we finish it this week. Memory is the hardest part. Once you understand memory, well, even if you don't understand memory, once we move to the next stuff, it's going to be a lot easier. There's a lot less in it, in most of it. Dynamic partitioning, deallocation, any idea?
The free table and then check it.
Yeah, we go to table and we mark it as being free. It's actually moved to the free table. It keeps two tables and then it combines them. It checks the one before it, the partition before it. Is it immediately next to it in memory? and the one after it. If either the one before it or the one after it are neighbors, or the three of them are neighbors, the one before it and after it and this new one, it will merge the neighbors into one bigger block. Okay, so if we had one big block here of 100K, and beside it there's another block of 100K. So we have now one bigger block instead of two of the total size of the two free blocks. So there's a bit of work involved in each, part of the dynamic partitioning system, a bit more complicated. And then that should bring back lost fragments. Every time a free block is allocated, let's say this free block has 400 kilobyte, and a program comes up and says, I need 390. So we give it 390, and the rest of it becomes external fragmentation. What's the definition of external fragmentation? How would you define it? If I say, what's external fragmentation?
So, really small memory blocks which cannot be used.
Exactly, yeah. It's memory block which is too small to be useful, to be used. But it's still missing one small bit, this definition. Any idea what the external fragmentation is? Is it small parts of unusable or memory that cannot be used? Any idea? That's not really the definition of external fragmentation yet. Any idea? How would you make that definition correct? Okay. What's external? Let me start it again. What's external fragmentation? How would you define it?
Small, the part of the world that's too small.
Yeah? Too small to be used. Then you stop. That's exactly what he said. Anybody wants to add anything to it?
The fragment those belongs to any program.
Exactly, and not allocated to any program. It's free, it's available. And that's what makes it different to the internal fragmentation. The internal fragmentation is also space that's not usable, but it's already allocated to some program. A program needs 100, but we say, hey, we have a block of 200, take it. That extra space is also fragmentation, but it's internal. And the difference between internal and external is that the internal is already given to a program. We cannot use it, we cannot take it from it until the program finishes. But the external, it's available to anyone else to use it, even though it's useless. But what we can do is we can take all those external fragmentations, even the dynamic partitioning says join them. Every time a program finishes, look at the one in front, behind it, or before it in memory, or after it, try to join them together. But sometimes you get too many fragments that are not neighbors, and things don't work, and that's why they went to the next system, which is called the relocatable dynamic partitioning system. And the relocatable uses a function, it's called compaction. Any idea what the compaction function is? Or what does it do? What is the compaction function? Guys, you need to know these pieces of information. I've been asking them every lecture. Make sure you understand them. Yes, if you don't, probably you won't be able to answer the memory part of the question in the final exam. All right. Well, let's just finish this last bit. Compaction. What's a compaction function?
Prevents empty user spaces and
It doesn't prevent, but it reclaims all the fragments, external fragments. How does it do it? Okay. Let me give someone else the chance. Yeah?
It puts all the memory.
It moves.
It moves out and moves the fragments to the other end.
Yeah. It moves all the used blocks or partitions to one end and all the unused partitions to another end. Now they are neighbors, it goes and joins them together. Right? So that's how it works. So try to understand and get the question. If you're asked, what is it? You don't have to explain how it works. Tell them what it is. What does it do? Tell them what's the purpose for using it. If you're asked how does it work, well then that's how it works. And what's the advantage of it? Or what's the problem with compaction? You know the compaction function? It goes around, looks for all these fragments, it keeps moving all the programs up to an end, all the free fragments to an end, and when it has them all in this end, it joins them together. So the purpose is that all these little memory pieces, the fragments, they become now one big block. Now, that's a great thing, but what's the problem with it? With compaction? Now a little, it's very slow. It affects performance. It's a very slow thing. You don't want to run it a lot. You want to minimize it. Okay. Right, okay, what else? So then we started, did we talk about page systems? Page memory systems? Did we talk about virtual demand page systems? No, we just talked about paged. Okay, what's paged system? Paged system would be system number 4. So we talked about three systems, and this is number 4. We talked about fixed partitioning, dynamic partitioning, and relocatable dynamic. Those 3, they have a requirement. The program must be loaded into memory. The full program must be loaded into memory. And the second requirement, the program must be loaded in one continuous allocation, in one continuous partition. You can't put half of the program in that part of memory and the other half in another part. No. So that's the old days. You must have the full program in memory and you must have it in one continuous space. Until paged system came. So now we have this, and this is known as the paged memory management system. And how does it work? The page system, it works like this. When a computer starts, anytime you're asked to describe any of those systems, you always must say what happens at the start when the computer is switched on. That's the initialization. And also you must then explain what happens when a request comes in or when a program finishes. So now this is how to describe page system. The best way to describe it, you say at the start, when the computer starts, the entire memory is divided into equal size blocks or partitions. We call them pages or page frames. The entire memory is divided into equal size. Remember, with the fixed partitioning, we divide everything into different sizes. So small programs, you can put them in small partitions. Big programs, you can put them in big partitions. How do we divide memory at the start in the dynamic partitioning? Anybody remembers? Anybody? Yeah? Anybody? In dynamic partitioning, when we start, we make the whole memory into one big free block. We don't split it. And then every program comes in and asks for some memory, we cut off exactly as much as it needs. But in page system, when the computer starts, we divide memory into equal size parts of memory. Reasonably small, they're not big, but they're not too small to become fragments. They are not fragments. They're a little bit bigger than fragments, but still, they're not really large. So, and we can modify. Next time computer starts, we can tell it, make memory a little bit big, make every page a little bit bigger, or a little bit smaller, depending. And my next question is, which one is better? Should we select big page sizes, or is it better to have small page sizes? But for now, let's just say we split memory into lots of pages of equal size pages, and we have a table that describes each page. And all we have to say is this page, we don't have to even know where it is. We just say page number 0, page number 1, 2, 3, all the way. And if it's free, we mark them all as being free. And we allocate the operating system as many pages as it needs, like every other system. We won't say that anymore, because from now on, every memory manager system will give operating system the memory it needs. Now, the rest of them are available for programs. Now, that's what we do at the start. Now, what do we do? The next step, the next thing you need to always to describe is when a program comes in. Here's a program comes in. Program 1 comes in. What do we do with the program? We also split the program into equal size pages. And the pages of a program are the same size as the page frames of main memory. Just for example, just for argument's sake, every page of the program is 1000 bytes and every page frame is 1000 bytes, one kilobyte. And let's say the program is, say, 4250 or 4500. Then it will have page 0, page 1, sorry, 3000. So 3500. So, and page 4. So we split this into 1000, 2000, 3500. That's what the program is. And we go into the table here and we look for any free tables, free pages in memory. So which of these pages in memory is free? And let's, for argument's sake, we found this one is free, so we put program number 1, page 1 here, and then, sorry, page 0 here. And page 1 is somewhere along there, program 1, page 1, and program 1, page 2, and program 1, page 3. And we have a table for every program. We say, okay, this is the table for job 1, for program 1, because memory manager needs to know where every page is, has to keep kind of where in memory. So this is program 1 table, pages table. So it says this program had 4 pages, 0, 1, 2, 3, and I put page 1, we put it, for example, in memory, in page frame number, I don't know, let's say 470. That's just the number of the page. And this one, for example, 510, page number, and this one, whatever it is, 578. These are the page numbers. And finally, the last page, we put it, let's say, in 602. These are page numbers on main memory. So the pages of a program are 0, 1, 2, 3, 4, 5. Most programs will have 5 pages, 10 pages, 12 maybe. But we have hundreds of pages or thousands of pages in memory. But they're not all free. How do we find out? Every time a program comes in, the memory manager will go down the table and look. Is there a free table here? I need 5 pages free. So it goes down and allocates the program, and it will write here where each page is located. So that's in 510, that's 578, and 602, and so on. Now, program execution, for example, starts here. And then maybe here the program says, I need page number 2. How does the memory manager know where page number 2 is? It goes to the table, program number 1, where's page number 2? There it is. Oh, it's in memory location 578. Page number 578. So it goes to page number 578 and start executing. But still, even page 578 is not an address. It's just a page number. What's the address? It needs to know the exact point, the address. But because pages are of equal size, they have some sort of uniformity. So we can go anywhere we want. We can tell you what address each page is. Remember, we said every page is 1000 bytes, for example. 1000 bytes, starting from 0 here. So from 0 to 999 is page 1. From 1000 to 1999 is page 2, and so on. So where is page 512? What address is it? All you have to do, page number 578, sorry. Page number 578 multiplied into page size. So you have the page number multiplied by page size, will give you the exact address. So now page number 578 times 1000, and so easy you can find out that it's memory location 587,000. 587,000. You go to that location, and that's exactly the start of that page. So it's so quick and easy. You don't even need to keep the exact address of every page. You can work it out on the spot very quickly. One operation, one mathematical operation, one multiplication, and that will get you the location. So once you know where that program page is, where did you put it in memory, which page number, you take that page number, multiply it to page size, and you'll find out exactly where it is. Okay. So, because of the uniformity, it made things a lot easier. So that's called the page system. So suddenly, we got rid of external fragmentation and we got rid of internal fragmentation. Is this correct? We no longer have external fragmentation. Why? Some people say, hey, that's a page, that's external fragmentation. No, every page is usable. If page is not enough, if one page is not enough for you, we give you 2. If 2 not enough, we can give you 4. We can give you as many pages as you want for your program. And therefore, pages are not fragmentations. They are not external fragmentations. So we don't have external fragmentation. Any program that needs 10 pages, we can allocate it. The good thing now is that they're not all in one continuous block. They can be in any location in memory, but it doesn't matter. We can jump anywhere we want. In fact, we don't just jump to the memory location, to the page, to the start of the page. So easy to go to the start of any page you want. Like if I tell you, where is page number 40? You say it's in location 40,000. You just multiply it into the page size. Where is page 13? It's 13,000. Now, that's so easy. But no, sometimes you execute a program and your program say go to function wherever it is, and it's in address, for example, instead of 0, you start executing, say it's an address, let's say 150, somewhere here in the middle of the page. How does this memory manager go straight to that point, that line number? Not the start of the page, the line number. So all it does, it takes, for example, and let's just make it easier, every page has 100 lines. Just assume every page has 100 lines. We know it has 1,000 bytes, but let's say every byte is, let's just imagine that. For the time being. So you want to go to this page, page number 2. You want to go to page number 2 and line number 28 or something like that. So you want to go to page 228. Well, this one, you go to this address, 228. Now the memory manager has to work out, it's already in page number 0, but now it's got this address. Go to this address. Where is which page? And where's the line? It's again another simple thing. Divide it by the page number instead of multiplying it. But let's say you divide this address that you need to go to by the page size or the number of lines. Let's say the number of lines here. Every page has 100 lines. So if you divide this by 100, what do you get? What's the result here of the division? 228 divided by 100. What's the result? 2 and 0.28, right? 2 is the right whole number, and 28 is a fraction. That's what's the remainder. And that's exactly what it found out, that line 228 is in page number 2, and it's offset 28 lines from the top of the page. So any address, it's another quick and simple, quick way to go to any location, not just any page. No, it can go to any line you want. If you give it the line number you want to go to in your program, it will divide how many lines are in every page, how many instructions, and it will get a number when it divides by the page size. And that number the whole number will indicate the page, and the fraction number indicates the offset from the start of the page. So now it knows, hey, we have to go to page 2. Where's page 2? It goes to page 2. It says, hey, page 2 is in memory. It's in page 578. Where is page 578? Multiply to 1,000, give you exactly the location. Now go down 28 lines out, and it goes exactly to the line you want. So page system is so simple, so unique, so beautiful. It works so quickly. You can go to any place. You don't have to save all this information, addresses. You can work them out on the spot, and it's fast, and it's all in main memory. And am I right by saying there's no fragmentation at all? We don't have any external fragmentation because every page is usable. If you need more, we give you 2 pages. Are you scratching your ear, or are you putting your hand up? Yeah. There is internal fragmentation. Whoa, where is the internal fragmentation?
The last page.
The last page, because remember, if this program, for example, we said it's 350 lines or long, or 3,500 bytes, the first one will be 1,000, 2,000, 3,000. The last page, when you put it there, always the last page of every program does not fill the page. Most of the time, not always, but most of the time, 90% of the cases, you never get exactly, sometimes you might get a program that divides exactly in page sizes, but most of the time, the last page of every program is not full. And if it's not full, then that space that's left, that we give this page to a program and doesn't need it all. Like the last page, see, this page would be, all the code would be filling the page. This one, the page would be full. This one, the page before. But the last one only fill a part of the page. The rest of it is not filled. And we call that internal or external fragmentation. Why? Yeah, because that page is allocated to a program. The program doesn't need it all. But because we allocate it to it, we call it internal fragmentation. But it's not a big problem, because the wasted space is less than a page. It's always going to be less than a page. And we know pages are not too big, so there's not too much wasted space. And now comes my question I asked earlier on. Is it better when we start at the beginning with page system, is it better to divide memory into big pages or small pages? So what do you think? Which one is better? Exactly. How do they save memory?
Because it reduces the fragmentation.
Exactly. So if we divide this into small pages, then that last page of every program that we said is going to have a bit of extra space, that space is even going to be smaller if we start with very small pages. So we have less internal fragmentation. So it's better to go for small pages. And maybe even if we go even very small, it might be even a better idea. What do you think? The smaller the page, the better. How, would we go even smaller? The smallest? Not always. Why not? What could be wrong with the very small pages? So every time, remember, we give for example, a program needs 3,000 memory. If every page is 1,000, we give 3 pages. If every page is only 100, we give it 30 pages, but still the same amount of memory. We're not wasting any more memory. A program will still take as much memory as it needs, whether that memory is 3 pages or 30 pages. We can still move reasonably fast between them. So what's wrong with small pages?
It's a lot more flexible, a lot more complex.
Yeah. So remember, when you at the start, when you set up memory and divide memory into pages, you need to know every page, is it free or is it busy? And therefore, you need to keep that information in a table. So if you have 100 pages, then you need a table that has 100 rows. If you have 1,000 pages, then you're going to have a table of 1,000 rows. If you have 100,000 pages, then you're going to have a table of 100,000 rows, and that takes memory. That eats away your memory, that table, to manage the small tables. So it's easier to manage few large tables than many small tables, because the table that you need to keep the information about pages will become too much if there are too many pages, far too many pages. So pages too big are not good. Why not? So, all right, so if very small pages waste our memory, so let's go for big tables, big pages. So if we go for big pages, then we're going to have less of them, and therefore we're going to have smaller tables. Yeah, but if you have very big pages, then that program will probably only need 2 pages. For example, we have a program that needs 4,500, and the page is 4,000. So it needs 2 pages. The first page is 4,000, and the other page is also 4,000, but it's only going to use 500 of it. So there'll be a lot of internal fragmentation. So if you have big pages, it's causing lots of internal fragmentation. So here it is. I'm just going to draw same memory. Instead of too many pages, we're going to just split memory into very large pages. Every page is 10,000 K. 10K, 10K, 10,000, 10,000. So a program comes in and says, I need 11,000. You say, okay, here's a page, and here's the next page, and that's all. The rest of it is all wasted space. So the bigger the page, the more wasted memory in internal fragmentation. So if you're asked a question in the exam, be careful. Is it better to divide our page systems in small pages or large pages? Don't jump and say, oh, large pages or small pages. You have to say, small pages have the following advantages and disadvantages. Small pages will reduce the internal fragmentation, but they will need a big table to manage them, and that wastes a lot of memory. Large tables are easier to manage, and they need very small table to manage them, so they save memory from that end, but they will waste, with every program, they'll have large internal fragmentation. So it's neither good to have very large tables, or neither good to have very large or very small. So we have to work out. And if you're asked, give me your recommendation for a good page size, there's really no recommendation. If you are the system administrator, you'll have to try it one day in your company. All the programs that come and run on the servers, say, okay, I'm going to go for page size, whatever it is, 1K. Right? And then see how many programs get executed, what's delays and all that. And then the next day, double that size or increase it a little bit and see, do you get better performance? Do you execute more programs on that day or less programs, and try a few different values until you find whatever suits your company that will execute more programs. So there isn't really a very good figure of what's a good page size. Now, what's the advantage of paged system over the dynamic and the fixed, the other 3 before? Now, first, programs don't have to be in one big location. We still have to put the full program in memory, but now we can put it in different locations, wherever we find. And then we also, the other advantage, we don't have any external fragmentation anymore. We still have a bit of internal fragmentation. So that's the advantage, disadvantage, but it's easy to manage. Well, we need slightly more tables now. We're going to need a table now for every program, not just the table for the pages. Like in the old system, we used to have maybe even 2 tables for the partitions, but now they're not partitions, they're all equal size pages. Well, still we need a table for that, but now we have an extra table for every program. It's a little bit extra complicated, but it works smoother and better system. So what's the problem with it? Why don't we continue with it? It's smooth, it's fast, everything happens in main memory, but still the problem is all the program need to be in memory. If you don't have enough memory, then you cannot run the program. So we still cannot, up to this point in time, up to the year 2000, you cannot run a large program. If that program is bigger than the memory of your computer, you will not be able to run it, even just one program. All the other programs, finish, stop them, and then run one program. You may not have enough memory to run that program, because that program needs more memory than you actually have in your computer. So that's really the only problem with this system. It's just, you still have to load the entire program into your memory. Okay, we used to put it in one block, but now we put it in many pages, but the problem is still there. You cannot run a program that's bigger than memory. And for example, you can maybe only run 10 programs, depending on how much memory you have and how big the programs are, give or take. So they came up with a newer system, and it's called, which number is this? 5. So we go for number 5. It's called Demand Paged Memory Management Systems. What does demand paged? That means we only give you pages upon demand. If you need pages, we give you. Otherwise, we don't give you all the pages at the beginning. And this is the first time where we actually don't have to upload the program in memory to run. Because they said, there's a reason. They said, why should we upload all the code? Some of your code will probably never need to execute. Remember, when you write a program, most of the time, your program doesn't all get executed. Imagine if this is, you write 40,000 lines of code. The program starts running here, and then you need to clear the screen and display a menu. You might have that function here. You say, go and do it, and come back again, and keep executing. And ask the user for the password. For example, there's another function here that gets the information, password and name from user. So, and so on. So do this. If the user gets choice A, go and do this function A. And if the user gets, and when you finish, come back. And if it chooses B, you go down and do function B and come back. And keep repeating this until you finish executing. And sometimes, if the user types in the wrong information, go to this section here, and this is the error kind of procedure. You display an error message to the user and say, hey, don't type numbers or don't type characters and all that. So some of your coding, let's say the user, you ask the user type in, they type in the correct name, the correct date of birth, they never made a mistake. Then you will never run this code, ever. Right? Maybe next time you run it, the user makes a mistake. Maybe you say, okay, if we want to print and if the file is too big, they call this message at but we never had that problem. The file was never big. Or if the printer is not available, display this message to the user. The printer was always available. So that part of your code is never executed. Yeah, it's good. You're a good programmer. You consider everything just in case the printer is not online. You go and check it, but sometimes that part of your code is never executed. That's why here they say we don't always need the program to be in memory to run. So if we can pick the parts of the program, the important parts, and we run them, and we can swap them out. So that's the idea of demand page. But in the past, they couldn't do it because they had tapes, and a tape is very slow. We'll be studying tapes maybe 2 or 3 weeks' time, but the major advantage, anybody knows what's the biggest difference between a tape and a disk, a hard disk, from operational point of view? Pardon?
A tape is sequential.
The?
A tape is sequential.
Yeah, the tape is sequential. What does that mean? From a performance point of view, if you want to read something somewhere here, towards the end of the tape. You have to keep reading, and the tape keeps rolling, and read it a bit at a time until you get to that. So it's slow. You cannot directly go to that point. And if after reading that part, you're going to go back and read something that you've already missed, already gone ahead, you can't just roll back to that point. You have to roll back the entire tape and start reading again. So, and it takes minutes. So it's not good for interactive applications. You know what interactive programs are for applications, for systems? You know what interactive systems are? Anybody remembers the interactive systems?
There are systems which are has really high response rate and critical.
Yeah, it's a system that has a quick response. That means the user says, give me this, it expects it in a second or two. But with tapes, you can't have that response in a second or two. The tape might take minutes to rewind and start again to read the information. So, but since then, they introduced these hard disks. And a hard disk is just a disk that spins, and the information is written in tracks, in circles on top of the disk, magnetically. And it keeps spinning all the time, maybe speeds of 15,000 revolutions per minute. And you have a head that reads, and the head just moves this range. If it wants to read something on the outside track, it just moves outside. It puts itself here, so the head is there. So that thing spins and goes under the head and picks it. If it wants to read something else, it moves there. So it only takes 1,000 of a second to move the head from one track to another. So even if the track is 100 tracks away, I'm at track number 1, I want to go to track number 100. It takes 1,000th of a second, so 100 each track, so 1,000th of a second is time. And as soon as it gets there, the data spins, goes underneath it and picks it up, so you can read in such high speed, like we're talking about 1,000 parts of a second. That's how fast you can read from a hard disk compared to a tape that can take minutes. So a tape to a hard disk is like the horse cart and a racing car. And memory to that racing car, or memory to the hard disk, is like that racing car to a rocket that travels through space. So main memory is very fast, hard disk is reasonably fast, but tape is really slow. So when they invented hard disks, they said, okay, maybe we can use them as memory. But no, they can't really use them as memory because they are still very slow. Remember, memory travels at the speed of electricity, the speed of electrons in wires, and that's about 2/3 the speed of light. So it's pretty fast. Hard disk, even though it's fast, but it's still a mechanical device. Nothing mechanical ever reaches the speed of electrons. No way. Still thousands of times slower. But it's better than nothing. So we cannot use it to execute programs, but we can use it as extra memory. And that's what they call virtual memory. So if you are asked what is virtual memory, the word virtual means almost real. It's not real, but almost there, right? So that's why they call virtual memory, that means almost real. Virtual reality is like almost reality. You know, when you put those glasses on and you start looking at playing games that you think you're really flying or swimming or whatever, then they call that virtual reality. That means you are almost in reality. Not there yet, but almost there. So that's what we call virtual memory. So we use the hard disk as virtual memory. So if your computer has a hard disk, then possibly part of it, since the year 2000, most operating systems, including Windows operating system, will say, all right, I'll take some part of the hard disk and I use it as memory. We use it as virtual memory. And usually in your setup, they'll ask you every time you set up Windows, say to you, how much? Well, there is a default value. Let's say, how much of the hard disk shall we take? 10%, 12.5%, or whatever it is, or we use it for virtual memory. So really, the hard disk, part of it is going to be used by the memory manager. Right. So now, this is how virtual demand page systems work. First, demand page systems are virtual memory. Now we know what virtual memory is. It uses main memory, but it also uses the hard disk as an extension of memory, as if it's memory. We know it's virtual memory. That means it's not really memory, but it's almost there, and it's good, and we'll use it. So, and how does the demand page system work? This is how it works. We go to when the computer starts. This is exactly every time you're asked about any memory system, you must first say what happens at the start. When the computer is switched on, main memory is divided into equal size spaces or partitions. We call them page frames. So each one of those here is known as a page frame. Pages, if you say pages, it's okay. I won't, there won't be, you won't be deducted marks. But remember, just to isolate them from, remember when a program comes in, it's also divided into pages. They are also pages. So just to differentiate between the pages of a program and the pages in main memory. They call the pages in main memory page frames. Now, these are all numbered, obviously, and there's a table that, tells you whether that page is free or it's busy. So initially, they're all free, all pages. All page numbers, page 0, 1, 2, 3, all the way. And also, the virtual memory is available there. Now, how does this work? Well, that's the initial. When we start, memory is divided into partitions called page frames. They're equal size, they're not too big, not too small. And when a program comes in, somebody says, execute this program, we move that program into virtual memory. We put the program in virtual memory. Virtual memory is almost, you can consider it unlimited, endless amount of memory, because hard disks are so big, you can have as much of it as you want. They're not great as far as speed is concerned. They're not like main memory, but they have the space. So we have lots of space. And so the program that needs to be executed is put in virtual memory. So that's what virtual memory there, this part here. So we put the program there, and I'm just going to show you what the program might look like. And the program is divided into pages, right, in virtual memory. So it's divided into pages, and the pages are numbered 0, 1, 2, 3, 4, 5, and so on. As many pages as the program needs. And of course, in main memory, we do have a table. So this is the table for the pages or page frame tables, and this is for the program page table. So every program also has a table for its pages. Now, we used to, remember, in the page system 0, 1, 2, 3, let's say this program has maybe 5 pages, 4, 5, 6 pages from 0 to 5. Now, initially, there's a status field. Now we need another piece of information. Is this page at the moment in main memory or is it not? Because remember, we can only run a program, the code of a page if it's in main memory. If it's not in main memory, we cannot execute it. So the memory manager now in demand page needs to know. And initially, they're all not in main memory. So no, there's none of these pages now in main memory. They're all sitting in virtual memory. They're not good, really. In virtual memory, you cannot execute them. And the memory manager now decides how many page frames it's going to allocate to this program. Will I give you 3? Will I give you 4? This depends on what the administrator will decide. We might decide, give it 10% or give it no less than 3. Maybe the program doesn't even need 3, but it only needs 2, give it 2. 3, give it 3. But then if it's any bigger, don't reduce the size, don't give it the full amount. Because remember, we don't want to use every program, give it as much as it needs. This is the main purpose for this. So now, let's, for argument's sake, for this program, we're going to give it 3 page frames. So we define them, whichever they are. let's say this one, and these are numbered 0, 1, 2, 3. Let's say 172 belongs to program 1, and 203 and page frame 220. So these are the 3 pages allocated to this program. Now, when we say start running, run what? First thing I need page 0. We always need the first page of a program. So remember, the program is in virtual memory. So the memory manager goes straight to the table and say, is this page, is it in main memory? So it checks the table and say, no, it's not. It's not in main memory. See, the table shows that it's not. Well, then let's go and bring it. But it has a small function that will handle this business. If a page is not in main memory, we call it page fault. So if a program needs a page and that page is not in main memory, that's a problem. They call it a page fault. And we call a special procedure in the operating system, and it's called page fault handler. Page fault handler. Like some programmer wrote a small function that, hey, if we have a problem, let's call this function. So this function, this is what it does. Right, now we've already know now page 0 of this program is not in main memory. That's it, we've established that. The next point, it'll go, the page fault handler, it'll go and check those 3 frames that are allocated. It's like you book, for example, you and your family and your friends are going somewhere to another city and you book 3 rooms in a hotel. So there are 3 rooms booked for us. And one of us walked to the hotel and said, can I have a key to a room? They say, hold on, can we give you a room? Maybe they're all full. They check, first thing they check, no, they're all free. So the 3 pages are free. Fantastic. Well then, yeah. So this is what the page fault handler does. Says, is there a free page frame allocated to this program? If the answer is yes, well then go and bring the required page. This is nice and easy and quick. So we bring this page, which is page 0, from the virtual memory and put it here. And now page 0 is in main memory. And we go and mark it here. Page 0 is yes now in main memory. It's no longer a no. And where did we put it? We put it in frame 172. So we know this is, the first 2 columns are like the old page system. Hey, page 0 is gone to page frame 172. If you want to know where it is, multiply it to page size, I'll tell you exactly where it is. But we'll assume we know. We just call now the page. So we just brought the first page into memory and say start running. So if this one start executing, it'll execute for a few seconds, then probably says, I need page number 2, for example. So the memory manager will, how does it know where page number 2 is? It'll go to the page table and say, where's your page number 2? Are you in memory? It says, no, it's not in memory. Well then, what do we call that? Page fault. So it calls the page fault handler. Page fault handler says, okay, you want page number 2. First, is there a free page frame in memory I can bring page 2 straight in? And it says, yeah, we still have 2 free page frames. So that's a quicker kind of thing. All right, let me go and copy page number 2. So it brings page number 2 and puts it in there. So this is program 1, page 2 is sitting here. This is program 1, page 0 sitting there. And start executing. This one might say, get me page 3. And say, of course, don't forget page 2 now is in main memory. So the memory manager marks it and it's sitting in 203. Now, this one needs page 3. Again, page 3 is not in main memory, so we call the page fault handler. So do we have a free space? Yeah, we have another page frame. So go and bring page 3, put it here. And now page 3 is in main memory, marked here by yes, and it's put into page frame 220. And it's executes. And then this one, page 3 might say, I need page 2. So the memory manager goes, check page 2, are you in main memory? Yeah, where in main memory? we're in page 203. Where's 203? Boom, moves you in a millionth of a second. It puts control here and you start executing. So if the paging is in main memory, one check in a table and one calculation, and it goes in there. So maybe 2 millionth of a second you're there and you're executing. There'll be no delay. As long as the page is in main memory, it's no delay, the required page. Now let's say this time page 2 says I need page 5. Right. Page 5. You need to remember this sequence when a page is requested. Memory manager goes to the page table and look for the program page 5. Are you in memory? No. What does that mean? It means this is a page fault. Call the page fault handler. Now the page fault handler comes out, say, right, I'm going to go and bring page 5. But let me check, is there a free frame? This program was given 3 free spaces. Right now, they're all busy. They have pages in them. So they're not free. We cannot just go and bring page 5 straight in. Now, if there's already a page in each one of those frames, then we have to take it out. We have to take one of these pages out. Either page 1, page 2, or page 3 has to go out. Now we'll pick one of those pages and we have to write it back to the virtual memory. So this is where things are a little bit slow. Before we had to run the hard disk and read. Takes a long time reading, relatively a long time compared to main memory. Now we don't just have to read. First we have to take this page out, write it out, and then go to page 5 and read it in its place. Okay, so we have now 2 kind of slow operations we need to do, not just one. So, and now there's also another decision to be made by the page fault handler, which is also normally influenced by the administrator. Which page would we take out? Because remember, okay, let's just follow with the normal operation. Let's say we said the first in, first out. So let's say this was page 0 was the first in, take it out. So we go to take page 0 out and write it to the hard disk in its virtual memory. Why do we write it? Because while executing, you could have changed, modified it. Maybe we could have had value x equal x plus 1, and so that data is modified. The code doesn't get changed, but the data does. So if it was modified, it has to be written out. Now we've written it out, we go to page 5 and bring it in. And now we have to mark page 0 is no longer in main memory. We mark it as it's not in main memory. We go to page 5 and we say, yes, it is in main memory, and it's in page frame 172. And we put control there, and we say, start executing. So the program goes execute. So every time a program has a page fault, has to go to sleep while we go and swap, bring in the required page. Once we put the required page, we give it and say start executing here, wake up, and wakes up. The program doesn't know how long it's been asleep. But the page fault is a slowish operation because you have to run the hard disk. The more page faults you have, the slower the program is going to get. So sometimes you say, right, let's take this page out. You take it out, you bring page 5 here. Page 5 starts working, it might say, give me page 0. You've just taken it out. You have to go and bring it back in. So sometimes you pick the wrong page to take out. We should always pick the page that most likely we will not be bringing back in for a long time. If you keep picking the wrong page, you take it out, the other one comes back in, take it out, then you're going to be slowed down 10 times or 100 times each time there's a page fault. So you stop executing. So your program is going to be run very slow. So we will look later on, well, next time, next lecture, which of these, there are policies in picking up which page would you take out. Some of them are better than others at certain situations. And we'll look at them. But the one I mentioned earlier, first in, first out, but not necessarily. That may not be always the best policy to take. But that's demand page memory system. It's a virtual memory system. What's the advantage of this system? Anybody can see the advantage for this system? What do you think? What's the advantage of this system over the page system? That's neat. Any ideas?
Save memory.
We save memory. So what, if we save memory, what's the real advantage to users? Huh? We can execute more programs. Is that what you said? Oh, no internal fragmentation. Oh. No, it's gonna be, again, the same last page of every program is still gonna have, like, these pages are of equal size, and when we split a program, we split it to equal size pages. There's always, the last page, you're always gonna get a few more extra bytes. Very rare that you get a program that splits exactly into the same page. But yeah, okay, maybe there's less because maybe that last page, we don't need to bring it in as much. Okay, I'll take it, but that's not really a major point. It's still considered like a page system that has that little fault of internal fragmentation at the end. But it has no external fragmentation. Any advantages over the page system? And you see, anybody can see any advantage of virtual page, demand page over page system.
Program larger than the memory itself will be executed.
Programs that are very, very large, bigger than our memory, we can still run them because we don't need to bring in the full program in. If that program is bigger than the memory you have, let's say we only have 1,000 pages, that program, it needs 1,020 pages. Normally we couldn't run it in the old systems because you have to bring the full program in memory, but now we don't. We don't have to bring it, we only bring 10 pages of that program. So this is the first time in history of computing that really now we can run a larger programs that are larger than main memory. We couldn't do it in the past. This is the first time when we started using virtual memory. And that's really the main advantage. Or we can also, even if we don't have a very large program, but let's just for argument's sake, we had 100 pages. And we had every program in the ordinary page system needs 10 pages. Then we can run 10 programs, 10 full programs. But using the demand page, every program, we say, will only give you 2 pages. 2 pages, so if you had 100 pages, we can run 50 programs. They will not be running as fast as the page system. The page system is so fast because it doesn't use hard disk at all. This demand page system, yes, we can run more programs because if a program needs 10 pages, we say we'll only give you 2. Another program needs 10, we say we'll give you 3. So we can execute more programs simultaneously. But the problem, every program as it runs, is going to have few page faults. Every time it has a page fault, that's a big delay of the program. So demand page systems can run bigger programs that are even bigger than main memory, or we can run more programs than any other system before, because if a system can only fit 10 programs in memory, hey, we don't have to fit them into memory, and therefore we can run 40 programs instead of 10 programs. So these are the 2 major advantages of demand page system. It doesn't have to, it can run programs bigger than memory, and it can run more programs than any other system in the past. Still, programs don't need to be put in one continuous space, and we don't have to upload the full program. Okay, if it's a small program, give it all the pages. If the program only needs 3 or 4 pages, you might say, let's give it 3 or 4 pages. So it'll say, we'll never have page faults in this program, so we have speed as well. But if it's too big, obviously, and then that's something else you decide, and we decide that's how many page faults do you give a program? We'll talk about that again at another time. So this is known as demand paged memory management system. It still has a bit of an issue. Page faults is the problem. What's a page fault? You look like somebody who knows what a page fault is. Anybody can define page fault for me? What's a page fault? Have a go. It doesn't matter if it's the wrong answer. I'm not. If a page is required or requested by a program and it's not in main memory, it's in virtual memory, we call that a page fault. So a page fault is a page is requested, but it's not in main memory. If it's in main memory, you just go straight to it and keep the execution. You don't stop executing. But if there is a page fault, it means you must stop. The program is put to sleep, and we go and fetch that page from the hard disk, virtual memory, and bring it into main memory. Anybody knows the steps, the process of a page fault handler? What does the page fault handler? What's the first thing it does? If we say to you, go bring us page number 7, what's the first thing you need to do? If you are the page fault handler, if you are listening to me there. Any idea? If page number 7 is not in memory, what do? You want to bring it into memory. We check, is there a free page frame? Remember, every program is given 3 or 4 page frames, and maybe they're still free. One of them is still free. It's like we book 4 bedrooms in a hotel, and there's a group of us going. Whoever goes, the first 4 will get the 4 bedrooms. The 5th person will tell them, you have to wait until somebody finishes or whatever. So same here with page frames. First thing the page fault handler will do, if we say, well, get us page number 8, we say, okay, do I have a free space to go and bring it and put it in? And if there is, if you go and bring it, and that's it. That's all it has to do. If there isn't, if we only have 3 page frames and they're all occupied by other pages, what do we do? What does the page fault handler do?
They need to decide which one to write out.
It will have to decide one of these page frames, with pages we have to take it out, and whenever it decides, it takes it out, writes it back to the virtual memory, and brings the required page from, read it from virtual memory, and puts it in this place, in the place which was free. Okay? This is the sequence that happens. If you're asked, what does a page fault handler do when a page fault occurs? Okay, so the disadvantage of this system. What's the disadvantage of demand page systems when compared to page systems? Remember, page systems, computer is divided, memory is divided into equal size page frames, and the program is divided into pages, and all the pages are put into memory. In the demand page, same thing. Memory is divided into page frames. Every program is divided into pages, but it's put in virtual memory. Only a few pages are put in main memory. What's the disadvantage of this system? Yeah. So it's slower. And the more page faults, what slows it down is the page faults. If you take a program that has 10 pages, you only take 3, put them in memory, and they all run and they never stop and they finish. Execution correct and complete without needing another page, well then it will be fast. But most of the time, no. Most of the time a program is 30 pages and we give it 3, so it's going to be swapping a lot of pages. And swapping pages takes a bit of time, and that's the actual delay. Now, there's another little problem. Let's say this is your code. Have you started writing programs? No. Do you know what a loop is?
Yeah, of course.
Yeah, of course. Yeah, but everybody knows what a loop is? Okay. A code in programming. Right, usually in programming, when you write a program, they get executed in sequential, one line at a time, one followed by the other. Sometimes you might skip over a line. If you say if x equals 0, do this line. else do this line. So sometimes you can do that or that, skip over some of the code. Sometimes you can use the while loop, while x less than 0, do all this, and this is the end of the loop. So you keep going around this loop until the condition, whatever condition. This is called looping. Loop, that means do this 10 or 20 instructions or 5 instructions and keep doing them until a condition. Here's a very simple code. X equals 0 while x is less than 1,000. Do x equal x plus 1 and end of while. So what does this code do? It puts 0 in x. It checks it. Is it smaller than 1,000? Yes, go in here in the loop. Add 1 to it, so x becomes 1. The end of the loop, you go and check again. Is it less than 1,000? It's 1. Yeah, then go in again. Add another 1 to it, so it becomes 2. You keep going in until x equals 1,000, then you skip and go out and continue. For some reason, you want to repeat something. Maybe print something 1,000 times or do whatever you want to do. Now, imagine if this is your code, your program, and you divided this code, we said, in memory systems and in virtual and demand page systems and page systems, we divide the program into equal size pages. Let's say the division came right in here. That's page number 4. And this is page number 5. The division came right in the middle of a loop. Okay, that's page 4, page 5, which is normal. You divide in division here, in demand paging and paging, we split the program based on size. How many instructions? Nothing else. No logic. Now let's say we're running demand paged. And we have few pages of the program, page 0, page 1, page 4, and page 2. So we have 3 pages of the program are in memory. Right now we are running page 4, there it is. And we got to the loop. And the loop says, hey, I need the next page, page 5. So page 5 is not in main memory, so that's a page fault. We call the page fault handler. Let's say the page fault handler comes in and says, okay, which of you guys here came in first or came in last? Let's say the last page that came in, take it out. Maybe the system administrator said, hey, if I bring 3 pages, 1, 2, 3, the last one, we probably won't need it again, get rid of it. So the last page, for example, here came in is number 4. So get rid of number 4, write it to the hard disk and bring in number 5. So now we have page 5 in. Page 5 has maybe 100 instructions, but it only goes to 1 instruction, add 1 to x and says while end. Of course, while end, it will be translated. That means go back to this line here. Where's this line? It's in page 4. So we need page 4. Is page 4 in memory? No, we just took it out. Then it's a page fault called the page fault handler. So page fault handler goes and say, let's bring page 4. Okay, do we have free space? No, we have page 1, 5, and 2. Okay, I'm going to take one of them out. Which one will I take? It's the last one that came in. Which one came in last? Number 5. All right, take page 5 out and bring page 4 in. So page 4 in starts executing. It doesn't go to the start of the page. We just bring it straight to this line. That's where it needs to go. So executes this line, says, what value is x? Is it less than 1,000? Compares it, yes, less than 1,000. Okay, go into this loop. The loop is in the next page, page 4. Says I need page 4. So page 4 is not in memory, it's another page fault. So we call it, and it takes page 5 out and brings 5. This is one of the first examples of frequent page faults. Why? Because we divide pages in this system based on nothing except size. We want them to be equal size pages, uniform pages. But sometimes that has a bit of a problem, a disadvantage. And it has a name. Can't remember now what the name is, but it's very frequent page faults. And if your program gets stuck into something like this, every time it will swap these two pages maybe 1,000 times. Every time it takes 2 seconds of a hard disk. That's 2,000 multiplied to 4,000 seconds. That's a very long delay for any program to be executed. So page fault, if it's frequent, it's known as thrashing. So if you're asked what is thrashing, it's frequent page faults, too many page faults. And that's a problem that demand page systems suffer from. Virtual systems that use page. And what causes it? It's caused by swapping the same page or two pages in and out too many times. What can cause it? I just gave you an example of what can cause it. It's caused because when we split the program, we don't pay attention. The split can come in the middle of a loop. That's not good news for page systems. Ideally, you should never split a loop. Ideally, if there's a function, keep it all in one page. So they actually improved this system. They said, this is the next system of memory system, just bringing you, the system to view them. They said, the next system, I think, is number 6. It's segmented demand page, systems. So instead of paged systems, demand segmented systems. So what do we do in this system? Is if you have, again, if they went back to the older system, like the dynamic system. So when you get a program, don't divide it into equal sized pages. It has a problem. Equal sized pages, they're great, they're uniform, they're nice for quick calculation, but for sometimes the split comes right at a critical point in the program that can cause a lot of problems. So they said, let's split this into a different way completely. Forget about page systems. Okay, but this system didn't really work for long. They found that it's not good, but I need to mention it to you because it makes up the following system. They said, you look at a program, split it in such a way, you never split a function or a procedure or a process or a loop. Okay, you can split it. So we're going to split it into the program into multiple different size segments. So a program is divided into multiple segments of different sizes. Let's say this is segment 1, 2, 3, 4. Now we won't stick long at this. I just want you to understand how it works. Now you want to put segment 1 in there, for example, or maybe this is demand. So let's say we're going to put 2 segments in there and leave the other segments out. So instead of demand paging, now demand segmentation. So we put segment 1 here and maybe segment number 2 there. Now they'll start executing, there'll be less page faults. Every now and again, segment 2 might say, hey, I need segment 4. So we might have to take segment 2 out and bring segment 4, and we might put segment 4 here. So now that part of memory became free, this is busy, that's busy, and so on. So we keep swapping segments. There will be less page faults or segment faults, there will be less faults. Because you never split, we'll never have thrashing. They will never be thrashing here. You know what the definition of thrashing is? You do? Okay. That's a good answer.
There's too many.
Okay. Do you know what thrashing is?
Frequent page fault.
Yeah, frequent page faults, yeah, thank you. Well, I was expecting yes or no as an answer to that question. Okay, but that's good, thank you. Right, so this is demand segmented systems. They suffer from less page faults, but you know what? They went back into the dynamic system. Now you have 3 blocks of different sizes, and you need to keep track of all these 3 different sizes, and they went back into external fragmentation, and they went back into compaction. So they improved performance a bit, but they caused a lot of other issues as well. So that was a good solution, but it wasn't a perfect solution. The perfect solution then, that's the one that's in use today. That's paged, segmented demand systems. Well, how does this work? Okay, it works like this. Memory, they went back to pages. There's nothing better than paging. With pages, they're uniform. It saves you a lot of hassle. But they know when you get a program, also split it into pages. But oh no, let's start. Split it into segments, sorry. You get a program, split it into logical segments. Why segments are good? Because they are logical. You never break a loop, you never break a function. But now, every segment, split it into pages, equal size pages. So this is segment 1. It has page 0, 1, 2, 3. This is segment 2, has page 0, 1. So some segments are bigger than others. This is segment 3, has 0, 1, 2, 3, for example, and so on. Now, anytime you want to upload, don't upload pages, upload segments. Right. So let's say we upload segment 1 and 2. You upload the full segments, but now in page terms. So you upload, for segment 1, you upload 0, 1, and 2. So you find free page here, free page there, free page there. That's program 1, segment 1, page 0. This is segment 1, page 1, segment 1, page 2. Now that segment 1 is all there. What about segment 2? Let's upload segment 2. So we found this one, segment 2, page 0, segment 2, page 1. And we are executing. Now let's say there'll be less page faults. But then after a little while, execution, this guy somewhere says, I need segment 3. Say, hold on, well, maybe we allocated you already maybe 6 or 8 pages. We can't give you any more pages. So you have to take some of the segments out. So you have, the memory is decided, will I take segment 1 out? All the pages of segment 1 go out and bring in its place the next segment. So we're still, even though we're talking about segments and we're dealing with moving segments, but the real movement and the calculation is always done on pages. So this is proved to be the best system so far. It gives us the advantage of paging, where everything is divided into pages and we can pinpoint every page wherever we want. But we never just bring one page. We bring a group of pages that belong to a segment, and segments are logically divided. You never split a loop between 2 segments. So if there's a loop, keep it all in one segment. So if we have to bring those 3 pages together. And we have to take them out, we take the 3 pages out. So this is the system now that's most up-to-date one. The advantage is clear. It uses main memory to the best. It uses virtual memory with less page faults or with less segment faults or page faults. It's more logically divided. But what's the problem with it? It's the extra complexity. Now every program, you need a page for all the memory pages. You need a table. But also every program, you need a table. It's called the segments table. And for every segment, you need a separate table with the pages in it. So, and you need to know each segment, is it in main memory, it is not. And if you have to move, you need to know where each of those pages are. So it's a bit extra complexity, but a lot better performance. So most of our communication will be on the first three systems, that fixed, dynamic, and dynamic relocatable, and the paged and the demand paged. This one is the icing on the cake. We won't be asking too much on it, but you just have the general idea of how it works. That this one works on segments. You split a program. Why? What's the difference between splitting a program into pages or splitting it into segments? What's the difference? Anybody can give me the difference? Which one is better? To divide a program into pages or segments? Segmentation is better. And because, why? You know the reason why? Because splitting something in segment, you take consideration the structure of the program, the logic of the program. Pages don't consider the structure or the logic of a program. You can end up putting a page right in the middle of a loop, for example. A loop of 2-3 lines, you put the page in the middle. It's better if you include that loop in there. So but if we take a segment and then divide it into pages, then we took the advantage of segments. That's the logic, the nice division, and also we take the advantage of page systems. What time do we finish at, guys? Okay. So we still have a lot of time, right? You haven't. Oh. Okay. Any questions? Any questions, guys? Okay, maybe I'll ask a few questions. Okay, let me close this and let me change the share.